right, so nuclear radiation measurements. How do we describe the detection and measurement of radiation? Okay, because obviously if we're around radiation, if we work around it, if we deal with it, if we're even miners and things like that of radioactive materials, there has to be a way to detect it. For one, obviously just detection, where is it at? But two, protection. How much exposure are we having? What happened? When is enough enough? So if anybody's ever had a CAT scan or X-ray, they always notice that the technician leaves the room. Well, why do they leave the room? To limit their exposure to the radiation, especially because they work with it every day. So one way is a Geiger counter. It detects beta and gamma radiation, not alpha. Okay, contains a metal tube filled with argon that produces the charged particles when radiation enters the tube. Okay, and argon is of course a noble gas, so it's inert. So this reaction allows for an electrical charge. So depending on how fast the reaction is, it'll tell you more or less gamma radiation. So Geiger counters look kind of like this. I'm sure we've all seen movies where they're like tick, 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 tick. So depending on how close to the source and how much radiation the source is letting off, this Geiger counter, this needle will increase so you can be aware of the radiation surrounding you. So when a radiation laboratory receives a radioactive isotope, the activity of the sample is measured in the number of disintegrations per second. So also known as the Curie, is the number of atoms that decay in 1 second for 1 gram of radium. Does it sound like a constant to me? Yeah, I think it is. All right. So we do have a constant. The SI unit of radiation is the becquerel, the PQ. So 1 Curie equals 3.7 times 10 to the 10th becquerels. Okay, so again, we've got a nice, we can go back and forth, right? We can go between the Curie and the becquerel. All right. So rad is the radiation absorbed dose that is measured. Measures the amount of radiation absorbed by a gram of material such as body tissue. So we've all seen movies where, I've been exposed to a dirty bomb, or I've been exposed to radiation. And they go, how many rads? Okay, so this is what they're talking about. It's the amount of radiation absorbed by a gram of material, such as body tissue. And body tissue is often used because we worry about a human being being around radiation. The SI unit for the absorbed dose is the gray, which is defined as the joules of energy absorbed by 1 kilogram of body tissue. And obviously, we're all different human beings, so there's kind of a standard set of body tissues. And when I mean we're all different human beings, body tissue, the amount of fat you have, how lean, protein, muscle, that all is going to affect this some. But 1 gray is nicely equal to 100 rad, so that's a very easy conversion. So if I said I had 500 rads of radiation, okay, that's my exposure, then we know it's going to be 5 grays in the SI units. The REM is the radiation equivalent in humans. Is a unit that measures the biological effects of different kinds of radiation. So beta particles, gamma particles, effects of alpha particles that do enter the body from different routes. So let's think about this. Can I breathe in alpha particles? Oh, most definitely. Okay. And the effects of high energy radiation that travels into tissue. Okay. So the SI unit is the sieverts, which 1 SV equals 100 rems. All right. So we have both English measurement and an SI unit equivalent. So the equivalent dose or REM dose is the absorbed dose of rads multiplied by a factor that adjusts for different forms of radiation. The same as absorbed radiation for beta and gamma radiation, which have a factor of 1. 10 times the absorbed dose for high energy protons and neutrons, 20 times the absorbed dose for alpha particles. So we got our biological damage, REM, equals absorbed dose times the factor, okay? So the absorbed dose of rads, all right, then versus our multiplication factor, okay? So we've got activity, so it's the Curie, the becquerel, and here's our relationship, okay? That's disintegration, how it breaks down. Absorbed dose, normally into a material, whether it could be tissue, but it could also be wood or water or things of that nature. So we either use the rad or the gray, and then the biological damage, which is either the rem or severt, all right? And then we've got all our correlating factors off to the side. So the Center for Disease Control and Prevention estimates that in the United States, 20,000 people per year are infected by, she'll kill me, Escherichia coli? Escherichia? Whatever, I'm not a biologist. Something coli. 500 people die each year from coli contamination. Oh, E. coli, there we go. Has been responsible for outbreaks and illness from contaminated food, ground beef, fruit, lettuce, alfalfa sprouts. I think Chi-Chi's, the food chain actually got shut down because their scallions were infected with E. coli and really just killed the chain. So the Food and Drug Administration has approved the use of 0.3 kilogray to 1 kilogray of radiation produced by cobalt-60 or cesium-137 for the treatment of foods. So cobalt pellets are placed in stainless steel tubes arranged in a rack. When they move through a series of racks, gamma rays pass through the food, killing the bacteria. So this is a good way of good use of radiation. But most people, if you were to say, yep, your food's irradiated, they'd be like, what? Radiation's in my food. No, it doesn't work that way. It's there to kill the bacteria. So when food is irradiated, it kills bacteria. It does not come in contact with the radiation source, so it's not like it actually touches it. And it does not become radioactive. This is the most common misinformation. When something is irradiated, it does not become like radioactive. It does not mean that your strawberry is going to go from approximately ping pong ball size to watermelon size because it's been exposed to radiation. But it does help decrease bacteria or eliminate bacteria, which actually increases the shelf life of the product when it gets to you. So it doesn't immediately go bad. So we're exposed to radiation every day from our food, water, environment, including potassium-40 found in potassium-containing foods, carbon-14, radon-222, strontium-90, and iodine-131 found in the air and in food. So, people are like, oh man, radiation is bad. Well, we're exposed to it every day. You get a sunburn, guess what? You've been irradiated, all right? You've been cooked, all right, through radiation. Medical sources of radiation include x-rays and mammograms, all right? So we do use them for medical uses, also for the treatment of cancer, all right? Exposure to radiation. Anything less than 25 rem usually cannot even be detected. In you, of 100 rem, the whole body produces a temporary decrease in white cells, okay? So this is where radiation treatment is dangerous for cancer because the people undergoing the radiation treatment can become very sick because you can have a reduction in white blood cell counts. Of greater than 100 may induce radiation sickness, causing nausea, vomiting, fatigue, reduced white cell counts. A whole body dose of 500 rem or more may cause death in 50% of people exposed. So, radiation can be dangerous, all right? And if we think of the bombs dropped on Hiroshima and Nagasaki, it wasn't the initial blast that killed all those people. I mean, it killed some, but it was the effects of radiation afterwards that really, really killed the majority of the people. So that's kind of radiation and some fun facts about how we read it, what kind of exposure does, and how it's used.